Welcome back to the present lecture. So, we are going to do the second order linear differential equations, both homogeneous and homogeneous cases in this next 2 or 3 lectures. The last 2 lectures in this module we have finished first order linear equations, and also we give some details about the differential equations which are exact, namely the exact differential equations. So, we will start with the second order linear differential equations. A general second order differential equation will have the following form: f of t y y prime and y double prime equal to 0. So, this is the most general form of a relation connecting the unknown function y equal to y of t, y prime of t and y double prime of t, and that is a general form. So, but what we are going to see is that, as in the first order case, if you treat this as a function of say y, y prime, y double prime, then we demand L is linear with respect to all these variables, with respect to y, y prime, y double prime. Just like in first order case where there was no y double prime, we had only up to this part, up to y prime in the first order case, and dividend. We do not demand, as like in first order, we do not demand any linearity with respect to t. So, we have linearity with respect to y and y prime and y prime. Then from the linear algebra, it is not a difficult thing, is a general form of linear equation, a general form of second order linear differential equation will have the form P naught of t, because we do not have y double prime, plus P of t y prime plus Q of t y equal to R of t. So, this will be the most general form of the second order linear equation. And again, as I told you in the first order equation, whenever there is a coefficient in the y double prime which vanishes, which will be singular type differential equations. So, the moment the highest order has coefficients which vanishes, which will not come in the regular category. So, in this thing we are not going to deal with it. Later you may see some singular equations in some other module. So, the general form we consider are more regular general form. We consider the form y double prime plus P of t y prime Q of t y equal to R t. So, we will have this is the equation which we are going to consider, which we keep on 1. So, this is our main equation with coefficients p, q and r. In fact, we have seen an interesting example in our module 1 when given the introduction about the spring mass response system and also RLC circuits, where P not P1, P, Q, R and T are constants, and see the impact of the second order and solution. All that results and how to find with constant coefficients, we will see it in this thing. So, the one of the thing, as I said again in the first order equation, the important thing is the superposition principle, which we are going to see. Superposition principle. What is this superposition principle? If you have two solutions of the homogeneous equation, if y1, y2 are solutions to homogeneous equation, solutions to homogeneous equation, that is L of y1 prime, y1 double prime. What is y1 prime in this case? We have y1 double prime plus pt into y1 prime plus qt y1 prime equal to 0. That is a homogeneous equation. So, when the equation in this case is here, if RT equal to 0, one is called homogeneous, one is called homogeneous, otherwise non-homogeneous, Okay. So, that RT equal to 0 homogeneous situation. So, that is what we are taking, RT equal to 0. So, similarly L of y2 prime, y2 double prime equal to 0. So, if y1 and y2 are solutions to your homogeneous system equation, then alpha y1 plus beta y2 also satisfies y equal to alpha y1 plus also satisfies L of y prime, y double prime. This is the superposition. This is the typical nature of the any linear system. So, that is what it will be satisfied. We exploit this to understand the solution structure of the homogeneous equation and non-homogeneous equation. One of the difficulties in unlike in first order equation, where we could completely determine the solutions to your differential equation, there is no general recipe to find the solution to your second order equation. So, we want to understand the structure of the solution space, but there is no way to determine the solutions, and that is what we are going to study in this situation. Regarding existence, this will follow from the general theory, which you will be studying, general theory, or one can also refer any book. For example, you can refer the book by Siemens to see a proof of existence. So, we are not going to prove the existence theory, but let me just state the existence theory. Assume P Q are continuous in the interval t naught to t, then there exists a unique solution to the initial value problem. I will explain what is the initial value problem here. Initial value problem, L of y prime, y double prime is equal to r with y at t naught is equal to some y naught, y at t1 is equal to y1. This y1 is not a solution, y1 is a constant. So, this is the, so why this initial value problem is that naturally coming. Let us look at the given system. So, we will not prove the existence, but existence can be proved from the general theory or from any other situation one can prove that general theory. So, but let me see why this initial value problem is very natural. How do you get that one? We can write a second order equation can be written as a system. This is also true for nth order equation. So, that is why I want to specify. We will recall all these things later when we study general system. So, put y is equal to y prime is v is equal to y prime. If you put v is equal to y prime, or in other words y prime equal to v, both are same, then from the equation you will get if you are substituting y double prime is equal to minus pt y plus qt. We are considering the homogeneous system. You can also write this also minus qt plus this is y prime. So, this is y, you can put this is equal to RT if you want it, non-homogeneous system if you want. So, if you put this in terms of V, this is equal to minus PTV minus QT y plus RT. So, if I write that this as a system y prime, y double prime is nothing but your V prime. So, you can write that if you combine it as a system. So, you have y V. So, you have a system V prime here. I can write it in the matrix form. So, you have your y here, you have your V here. So, what do you want to get it? First you get it V here. So, you want y prime should be V. So, this will be 0, this will be 1, and then if you want V prime, you want V here, y here. So, you have minus qt here, minus pt here, plus you have your RT, that will be of the form 0 R. So, you see here. So, this can be written in a nice form. Later you will see, if you put your x is the vector, y v, this is nothing but. So, we will get a system of the form dxt by dt is equal to atxt plus some gt, where gt is equal to 0 RT. So, you can write it as a system of equations. This can be done here. So, if you recall the first order equations, so you have two. So, we have two first order equations, for y and v. Thus, we need two initial conditions. Thus, we need two initial conditions. Y at t naught say equal to y naught, and v at t naught is the same as y prime at t naught say is equal to y 1. So, that is why the initial condition, and we have seen in the first order equation, when you study, because of the integration there is a constant. When you integrate out, you have a constant, and if you want to fix that constant, you need one condition. But we have two equations, two first order equations. In principle, you have to integrate two unknowns y and v, both requires one condition each. So, the initial value problem with the two conditions for second order equations is quite natural. But again, there is a speciality in the second order equations. Second order equations can also be considered, such equations L equal to say RT can also be considered in an interval, say AB, in an interval AB, and the conditions at the end point conditions y a, y at p can be prescribed. There are many interesting physical problems where it comes as a second order equations in an interval with the boundary conditions. These are called the boundary value problem. and we may not go an elaborate study of boundary value problems in this course, but we may give 2 or 3 lectures about the boundary value problems in some other thing. But in this particular module which I am going to do it about the second order linear equations, we will not deal with boundary value problems, and this is for the remark to be this is the remark which I want to make it. So now let us go to the, so we will classify into thing. So first we will start with the homogeneous second order linear differential equations. So let me give a notation: homogeneous second order linear differential equation. So let me call once again your differential equations for that. L of y, y prime, y double prime is equal to y double prime plus pt y prime plus qt is equal to 0. So that is why what we are going to study. So as I said, the other remark finding explicit solutions is difficult in general. Finding explicit solutions to this, let me call this 2, explicit solutions to is not possible always. This was not the situation in first order equation, not possible always. What I am trying to say that there is no general recipe to solve these equations in general with general p and q, but when p and q are constants, which such equations are known as second order equations with constant coefficients, which you already seen in module 1 of that spring mass dashboard system RLC circuits. For that we will have an explicit method of solving it. But when the coefficients are functions of t, since there are no general methods to do it, there are no general recipe to write down the solutions, we need some methods. So in this module, in the next lecture or something, we will also introduce 1 or 2 methods to find it, but they may not cover everything, but it tell you in certain situations we may be able to find the solutions. So the first main thing in this particular lecture, today's lecture, is to understand the solution structure. Can you tell me, can you tell us, or can you find some property of the solution space? And that is what we are going to do it, and we have the following proposition. That is what first we are mainly going to prove this proposition in this lecture. So let y1 keep y2, this not the initial conditions. So please give y1 and y2 are functions of t, y1 equal to y2, so it's not the initial condition, y1 equal to y1 of t, y2 equal to y2 of t, be any two solutions of 2. Then this is nothing but a superposition principle which I already explained. Then alpha y1 y equal to alpha y1 plus beta y2 is also a solution to 2 for any scalars, for any alpha beta belongs to R. This is a superposition principle which we already proved, but the converse is also converse in some sense. If suppose y1 y2 are independent solutions. So, you understood the concept of are independent solutions of 2. So, earlier case we are not demanding y1 and y2 are independent, any two solutions you take it, then its linear combination is also a solution. What the converse is that y1 and y2 are independent solutions, y1 that means as a function 2 function set, it is an independent set, are independent solutions of 2, then any solution, that means a general solution, that is a general solution We are not talking about the initial value problem, we are discussing about the solutions of there are no initial conditions prescribed so far. Any solution y of 2 can be written in the form y equal to alpha y1 plus beta y2 for some y1 by 2 for some alpha beta belongs to R. So, this shows that every solution y of this homogeneous equation you can write it as the linear combination of two independent solutions. This actually, let me make a remark before going to the proof. This is actually a very fascinating and remarkable result, in the sense that even though the solution set is a set of the solutions, any solution is something like twice differentiable functions, hence it will be a subspace of subset of some C2 space, twice differentiable space. And first result what it says that if y1 and y2 if you take any functions as a solution set, the first part of the result that alpha y1 plus beta y2 is also a solution shows that is the first part of the proposition tells you that that set is actually a linear subspace. The second thing say that if you can find two independent solutions from that set, then every solution in that set can be a linear thing. This is shows that even though the solutions set stays in an infinite dimensional space, its actual dimension is less than or equal to 2. So, this is the remark. If S is equal to the set of all solutions to 2, then S is a linear space. S is a that is a very important fact, that is a superposition principle, that is how it is defined. And the remarkable other thing is that S is a linear space and dimension of S is less than or equal to 2. What we are eventually after the proof of the theorem we will see is that in fact the dimension of S is equal to 2, but the proposition right now do not say that the dimension is S is less than or equal to 2, because if you assume there are two independent solutions, then that two independent solutions are good enough to determine any other solution. But we will actually produce using the unique existence, you can actually produce in theoretically two solutions. But the unfortunate or difficult part is that we do not know in general, or there is no general recipe how to get to that two independent solutions. That is why in the second order things you require methods and tricks to find the solutions. So, with this remark let me go to the proof of the theorem. Proof is not really difficult, only we have to prove one part. So, assume y1, y2 are independent solutions. Independent solutions. That is, I am repeating again, as in the L of y1, y1 prime, y1 double prime is equal to 0, L of y2, y2 prime, y2 double prime is equal to 0. So, we have given that. So, what we have to prove? You have to prove that if y is any solution, to the homogeneous equation 2, then you have to produce there exists alpha beta belongs to R such that y is equal to, y means y of t is equal to, alpha is a constant, alpha into y1 of t plus beta into y2 of t for all t. So, what are the things given to you? You are given y1 is given to you, y2 is given to you, y is given to you, and you have to determine alpha and beta, and then that should satisfy for every t. So, if a equation to be satisfied by every t, it should also satisfy for any t. So, in particular it should satisfy at t naught. In particular y at t naught, this is given to you, y is given and y at t naught is given. Y at t naught should satisfy alpha at y1 at t naught plus beta at y2 of t naught. So, you see, so you have a equation, but you have to determine two unknowns and alpha and beta. So, you need two equations. Right now you got one equation, but now differentiate the equation, differentiating equation y t, differentiating this equation, we get y prime of t equal to alpha y1 of t prime of t plus beta y2 prime of t. That implies y prime at t naught, which is also given to you, because y t is given to you for all t, is equal to alpha y1 prime at t naught plus beta y2 prime at t naught. So, we have two equations, you see. So, you have one equation here and you have another equation here. So, you have two equations for two unknowns. So, the question is that whether we can solve for alpha and beta, and that is what we are going to see. So, what are the equations? So, let me write down the equations in the matrix form. So, if you write down your equation in the matrix form, your job is to find alpha and beta. You have alpha here, beta here, and right side you have y1 at y at t naught, you have y prime at t naught, and left side you have y1 at t naught, y2 at t naught, second entry, here y1 prime at t naught and this is y2 prime at t naught. So, if you want to solve for alpha beta uniquely, if we have to solve alpha beta uniquely, we need the matrix to be invertible, this motivates us to introduce the Wronskian. We call this Wronskian, but introducing that matrix is the motivation. Introduce the Wronskian W as a function of t, but depends on y1 and y2. So, we are not treating w as a function of t, y1 and y2, we are writing w of y1 and y2 to represent that it depends on y1 and 2, but as a function of t we do that. What is my, so this is also denoted by wt, unless there is no confusion we just introduce it at wt. So, what is your wt? Wt is equal to determinant of y1 at t, y2 at t, y1 prime at t, y2 prime at t. That is nothing but y1, y2 prime at t, everything at t, minus y1 prime, y2 prime, not y1 prime, this is y2 prime and this is y1 prime, y2 at t. This is the Wronskian determinant of that one. So, we need to prove, so therefore, we need to prove w at t naught is not equal to 0. What is given to you if y1 and y2 are independent. So, under that assumption, if y1 y2 is an independent set, is independent, you see. So, as long as we are given this assumption, we have not used this assumption, we are going to. But the interesting fact, we prove, claim, which we are going to do soon, claim we not only prove if y1 and y2 is independent, we not only prove that wt naught is not equal to 0 at t naught, wt itself not equal to 0 for every t. In other words, wt will be either identically 0 or wt is never 0. So, claim w is t not equal to 0 for all t together, not just at t naught. Every t we prove that whenever, if, that is not very surprising, because independence at all thing y is independent. So, this is in two steps. First we will show that wt is either w is either identically 0, for that you do not need independent, either it will be identically 0 or it can be never 0, will be seen immediately, and then we will show that in the case of independence it is not 0. So, that is what you have to show that. So, first we show w is first we show either w identically 0 or w is never 0. So, here is a bit of thing. So, let us call w once again. What is your wt? Wt is equal to y1 t y2 prime of t minus y1 prime of t y2. You differentiate with respect to t, you get w prime of t is equal to y1 y2 double prime minus y1 prime y2 prime. Here y1 prime y2 prime minus this is plus y1 double prime y2. So, this get cancelled, that is nothing but y1 y2 prime minus y1 double prime y2. Now, use y1 and y2 are solutions, use y1 y2 are solutions, y1 y2 are solutions. So, if you use that fact, for example, you will get y1 double prime is nothing but, if you go minus pt y1 minus qt, if you take it to the right side, and y2 double prime is equal to minus pt y2 minus qt. So, if you substitute this here, you get y1 into minus p y1 by skipping t minus q minus y2 into y1 double prime, this is y2, and y1 double prime is minus p y1 minus q. So, this this term p, this is plus p y1 y2 is plus p y1 y2, this is that is something wrong. Oh, I am sorry. So, there is a y1 prime there, here is a prime there. So, this is p y2 prime, this is p y1 prime. Now, it is correct. So, there is y1 prime is missing, yeah, that is why. So, you have your, there is a q y1 here. So, I am missing that certain terms here, here y2 here. So, I have y1 here, y2 here. So, let me write properly. So, you have q y2 here, and here I have q y1, you see. So, this is second term is minus q y1 y2, here the second term is plus q y1 y2, that get cancelled. So, here you have minus p outside here, and you have y1 y2 prime, y1 y2 prime, this is plus y2 y1 prime, that will be minus, you will have y1 y2 prime minus y1. But what is this y1 y2 prime minus if you look at here y1 y2 prime minus y2 y1 prime is nothing but p, that is nothing but w. So, you have a nice equation for w, therefore, w satisfies the Wronskian w satisfies the first order equation w prime plus pw is equal to 0. So, that shows immediately w is a first order equation, homogeneous linear equation, and that implies immediately your wt is in terms of the integral. Immediately you will see that wt is equal to c integral of pt dt. You see your correct equation to be done. So, you see w satisfies this equation, and in this case this part is can never be 0. So, the w can be 0 only when your constant is 0. So, when the constant is 0, wt will be identically 0. When the constant is non-zero, then the wt can never be 0. So, the first part what will show that the result that w is identically 0 or w is never 0 is thing. So, you see, so to prove the proposition, you want to show that we need to prove wt naught is not equal to 0. So, this claim is fine. So, W is not equal to 0. Now, you have to use this fact. What we are going to is that either what we have just proved is that either W is identically 0 or W is never 0. Now, what we have to show is that W is identically 0 only if y1 y2 is dependent, and W is never 0 if y1 y2 is independent. So, that is the next claim to be proved. That proves your theorem as well as the proposition. Everything is complete the moment we prove this proposition. So, the first proposition is proved if we prove this proposition. We will give an argument, we use the uniqueness argument. W is identically 0 if and only if y1 y2 is dependent. We give a proof because it requires one part is trivial, this part is trivial. Why that part is trivial? If y1 y2 dependent, y1 y2 dependent, then either y1 is a multiple of y2 or y2 is a multiple of y1, either or both. Either y1 is a multiple of y2, k is a constant, or y2 is a multiple of y1. In both cases you can immediately, both cases W t is, what is W t? It will be k into same. So, it will be k into y1 prime minus y1 prime, because y2 is a multiple of. So, y1 into y2 prime is nothing but k into y1 prime is equal to 0. You see W for all t. So, the converse part is the non trivial part, that this part you have to prove it. So, assume W t is equal to 0 for all t, whatever it is in the interval, for all t in an interval, that is enough. You want to show that, say the interval t naught to t, that is all we are proving it. So, we are so to prove that, this is what you have to prove that y1 y2 is dependent. So, how do we proceed? So, let us proceed slowly, not very difficult, the proof. Suppose one of them is identically 0, then there is nothing more to prove. Suppose y1 identically 0. So, if a set contains a 0 function, that set is necessarily dependent, y1 identically 0 or y2 identically 0, then it will be dependent, then nothing to prove. Clear that point? Because if one of them is a 0 function, we do not have to prove anything. So, we can assume that, so we can assume without loss of generality, y1 not identically 0. I am not claiming that y1 is never 0, y1 can be 0 at some point, the identical 0 is not allowed, y2 not identically 0. So, since y1 not identically 0, there exists some point, there exists a point, say some t tilde in this interval t naught to t, such that y1 at t tilde not equal to 0. But now use the argument of continuity. If a function is not not equal to 0 at one point, then that function is not equal to 0 in a small interval. Yeah, so we will do that. That implies by continuity there exists an interval CD, there exists an interval CD, of course contained in T naught T wherever it is, and of course T tilde, these are all not important right now in CD, because such that y1 at t not equal to 0 for all t in CD. You see, so what we are using just continuity of the function y1. If a function is not equal to 0 at one point, it is not equal to 0 in a neighborhood of that point, and that neighborhood I taken to be CD, that is all, nothing more than that. You do not need anything to be taken, that is a simple analysis problem. Now consider, this is the only trick we have to follow carefully. Consider so we are working in the interval CD, nowhere else. Consider the interval CD. So we are doing all analysis in CD right now. Okay. Consider the W is identically 0 and everywhere. Therefore, 0 is equal to Wt by y1 square. This is something a construction, and this is allowed because for t in CD, on CD y1 is not equal to 0, so this is allowed. So now you write your, this is y1 y2 prime minus y1 prime y2 by y1 square. That is nothing but, that is where y we use that y. You can also work with y2, that is nothing wrong, d by dt of y2 by y1. Therefore, d by dt, this is why we need an interval, not at just one point claiming d by dt is not enough, we have to claim in an interval. So, d by dt of y2 by y1 is equal to 0 in an interval, that implies y2 by y1 is equal to a constant in CD, that is important, constant in CD, or y2 of t is equal to k y1 t for all t in CD. Now, this is where you have to use cleverly the initial value problem has a unique solution. Now, consider y1 is a solution to the homogeneous problem, y2 is a solution to your homogeneous problem. So, whenever you have a solution to your homogeneous problem, any multiple of that is also a solution to your homogeneous problem. Therefore, ky2 is all, ky1 is also a solution to your homogeneous problem, ky1 is also a solution to your homogeneous problem. Solution to your, that is y2, a solution to homogeneous problem. So, but y2 is ky1 in that interval. So, ky1 is a solution to your homogeneous problem and y2 is a solution. You take these two things, this is a very subtle argument. ky1 is a solution to your homogeneous problem in t naught to t, y2 is also a solution to your homogeneous problem in t naught to t, but y2 and ky1 coincides in CD. Since it coincides in CD, its derivative will also coincides in CD. So, you have two solutions to your homogeneous problem with the same initial data. So, repeat that, y2t in particular, y2t is equal to ky1t in CD. So, y2t is equal to ky1 to ky1t. That implies in particular y2 at C, any point you can fix it, C is equal to k y1c. Now, this is equal in an interval. I can differentiate this one, y2 prime of t is equal to k y1 t. These are all happening in CD, these are all happening in CD. But when I say that this is a solution, it is happening everywhere. So, y2 and k y1 is a solution to your homogeneous problem in the end everywhere, say t naught to t. But what is happening, this is in a CD. So, that implies y2 prime at C is equal to k y2 at C. So, now you see you have two solutions y2 and k y1. Thus, we have two solutions, y2 and k y1 with the same initial data, What are the initial data? You need to understand two initial data, y2 at C. I am thinking C as my initial data, that is nothing wrong in that, y1 at C and y2 prime at C is equal to k y1 at C. See? Therefore, by uniqueness y2 and k y1 has to be the same everywhere. That is what the initial value problem tells you. If you have two solutions in an interval for the homogeneous equation with the same initial data means y and y prime, then that solution is unique. Here we have produced two solutions y2 and k y1 in the full interval, but with the same initial data at C. So, the by uniqueness. So, that is what the uniqueness argument properly, uniqueness y2 t is equal to k y1 in the entire wherever this exists t naught to t, you see, for all t. And so, that proves the proposition, this proves the proposition. Once it proves the proposition, so let me recall, so let me consolidate once again. What we have done so far in the proposition in this hour, we have two, if we take two independent solutions, then that generates all the solutions. In fact, what we have done is that dimension of S is less than or equal to 2. That is what we have proved that. So, but what we will be soon see is that the dimension of the next proposition which you want to do that, let me do that theorem before I complete this lecture. Theorem, S is the set of all solutions to the homogeneous equation, please keep that in mind. Dimension of S is equal to 2. That is the theorem. The proof is now not difficult. The major part of the proof is already done, proving dimension of S is less than or equal to 2. To prove, we have to just produce two independent solutions. Do not get confused when I am producing two independent solutions, it is only a theoretical production. It does not give you the method to how to find it. You can solve it, you can solve it, because we do not know how to solve the equation. So, let y1, y2 be solutions to the initial value problem. Now I am considering an initial value. The idea is that you want two independent solution. The best method to get independent solution, you put your initial conditions as independent vectors. The moment you put your initial conditions as independent vectors, y1 at t naught and y2 at t naught, y1 prime at t naught and y2 prime at t naught, that will be independent, and hence your the solution itself will be independent. So what we will have? L of y1 prime y1 double prime equal to 0 with the initial condition. The easiest way to put the basis element y1 at t naught is equal to 1, y2 at t naught is equal to 0, and then you prove L of y1 to y2 prime y2 double prime equal to 0 with y2 at t naught is equal to 0, you see, and y2 prime at t naught is equal to 1. So, by uniqueness there exists y1 and y2, by uniqueness there exists unique y1 y2. We need only to show, we need to show y1 y2 is independent. How do you show y1 y2 is independent? Just compute the Wronskian independent. So, you just compute the Wronskian. What is the Wronskian Wt? Wt is nothing but y1 prime y2 prime minus y1 prime y2. And what is W at t naught? W at t naught is equal to y1 at t naught, that is 1, y1 prime at t naught is equal to 1. What is y1 prime? This is this is y1, and y1 at t y1 prime at t naught is equal to 0, and y2 at t naught is equal to 0, that is 1 not equal to 0. So, that is trivial. So, you have your two independent solutions which satisfies the solutions. So, what we will be doing? So, we have shown that the dimension of S is exactly equal to 2, and the interesting fact is that this theory you can also extend to general nth order equations, and you can see that the nth order linear equations with the constant coefficients has n independent solution, and the dimension of this space will be n. We do not do it here, but the same procedure. You can take the basis elements, you take in n dimension, you take the basis elements, canonical basis elements E1, E2, etc. En. For each Ei you solve, and then you prove that that solution set is independent, which will not do it, but the same principle works there to see that solution space is independent. So, tomorrow in the next class we will be giving few more things. In the next 2 lectures we may need it in this module to complete the second order linear equation. We will be doing equations with the constant coefficients, and we will also discuss something about non-homogeneous situation, and we will try to understand the solution structure of the non-homogeneous equation. Thank you.